and welcome to Math World. Today we're going to talk about quadratic systems. Alright, so it's going to start to feel like it's a little complicated at first, but it's a lot of stuff we've already learned just kind of, grouped together. So we have already learned about quadratic functions and how to solve them, and we've learned about linear systems. A system means more than one equation. So in this chapter, we're going to have more than one equation, and one or even more than one could be quadratic. So for example, here are two functions where y equals x squared plus 8x plus 5, and this is a linear one of y equals negative 2x plus 5. These are two separate equations, and that makes it a system. And in order to solve this system, you have to find the xy pair that is true for both equations. So we're going to be looking for a solution. We know how to solve a quadratic equation. We learned a lot of different ways for that, and we've learned how to solve a linear equation given an x or y. But what is the solution that's for both of them? What is the xy pair for both of them that will be true? All right, so there's a couple different ways we can attack this. We can try to just kind of use the algebra methods we've learned and look at the equations themselves. We'll look at that. But if we really break down the foundations of what it means for these two equations to have the same xy coordinate, that means that on the graph or the table, they'll be the same as well. So we can actually visually see the solution on a graph and identify it in a table. So let's start with the hardest one, which is the equations. Just using these two equations, can we figure out when they will meet on a graph? When will they share an xy pair? And we're going to use our substitution method essentially. When we learned back in the linear systems, is that if both of these equations are equal to y, if x squared plus 8x plus 5 is equal to y, and negative 2x plus 5 is also equal to y, then they're equal to the same value, meaning they are equal themselves. And what that allows us to do is it allows us to set up an equation that says x squared plus 8x plus 5 is the same as or equal to negative 2x plus 5. It allows us to set that big equation up, where this quadratic equation is equal to the linear equation. They look different, but when they are equal, that will be our solution. So now can we figure out what x value, there's no y value anymore, what x value would make this equation true? Well, now we're going to use all of our solving skills that we've learned. This has a quadratic in it, so we know when solving quadratics, we want to set it equal to 0. And right now, this quadratic expression is not equal to 0. It's equal to negative 2x plus 5. So let's set it equal to 0 by using inverse operation. We can add 2x to both sides of the equation to get rid of that negative 2x. And as we go through this process, again, it feels a little complicated at first, but it does make sense foundationally what we're doing here. I am trying to set this left-hand side equal to 0. The negative 2x plus 2x will go away, leaving just a positive 5. And I can subtract 5 from both sides. And that leaves me with the equation x squared plus 10x, 5's go away, equals 0. Now that my quadratic equation is set equal to 0, I can solve it a number of ways, with the quadratic formula or completing the square. In this case, I think the easiest way would just be to try to factor. You see there's an x squared and x. I'm going to factor out a GCF of x. I can divide both of these terms by x, meaning x will be one of my factors. And my other factor, divide x out of that x squared leaves x, and divide x out of that 10 leaves just 10. Dividing x out of the 10x leaves just 10. And so this expression, x times x plus 10, is the same as this. It would multiply to go back to the original. And now that I have two factors that are both equal to 0, we learned you can solve them each individually by setting them each equal to 0, and that would give us the answer for x. So in this case, x, this factor, equal to 0. Well, that one's kind of done. It just tells us x is 0. But also x plus 10 could be 0. Remember, if either of these factors equals 0, it will make the entire expression equal 0 because of multiplying anything by 0 is 0. And so when I go to solve this little mini problem, I get x equals negative 10. So x could be also negative 10. X could be 0 or x could be negative 10. And it's normal for us to have two solutions when solving quadratics because that's just kind of how it works. So let's see if these x values are true. Do they give us the same y value no matter which equation I plug it back into? So let's look back at our original equations. Alright, so one of our solutions was x is 0. Let's go ahead and plug that into this first equation. If x was 0, we'd have 0 squared plus 8 times 0 plus 5. In that case, 0 squared is 0, plus 8 times 0, that's 0, plus 5, that would equal 5. So if x was 0, the first equation would be 5. What about the second equation? In the second equation, we said it was negative 2 now times 0, if x is 0, plus 5. What does that make? Well, negative 2 times 0 is 0, and 0 plus 5 is also 5. So, and these were y values that we were trying to figure out. If x was 0, y is 5. That means one of our solutions will be 0, 5. Remember, we want our solutions written as an ordered pair. Because remember, the solution is an xy pair that is equal for both of them, not just the x value. So one solution would be x of 0, y of 5. That is one possible solution to this system. There could be a second one, though, because we found out that x could also be negative 10. So now let's try and see what happens if we plug in negative 10 into both these equations. Will they be the same? Let's go ahead and try it for the quadratic equation first, and I'm going to give myself a little more space here. So we have y equals x squared, but wait, x is not, we know x is now negative 10, so we'll say negative 10 squared. And I'm going to put in parentheses because we want to make sure that entire negative 10 gets squared. Plus 8 times negative 10 and plus 5. All right, a little more math here, so I'm going to try to write out more of it. Negative 10 squared, that's negative 10 times negative 10, that makes 100. Plus 8 times negative 10, that will be negative 80. And then plus 5. All of this together, 100 plus negative 80, that's going to make 20. And then plus 5, that makes 5. Oops, sorry, not 5. That makes 25. I'm looking at too many 5s here. 20 plus 5 is 25. So if x was negative 10, y would be 25. Okay, let's keep that in mind because it has to work for the second equation too. It has to work for this linear equation. So let's go ahead and plug negative 10 into the linear equation and see if that one gives us the same answer of 25. So if y would equal negative 2 times negative 10, I'm pulling this right from this linear equation up at the top, and then plus 5. All right, well, negative 2 times negative 10, that makes positive 20. And then when you add 5, well, yeah, you get 25 again. So we know our other solution that will give us the same xy. Remember, solution's an xy pair that works for both equations is going to be negative 10 and 25. So let's put that in blue again. Negative 10, comma, 25. That is a solution. All right, so we solved this system of equations, one being a quadratic, using algebraic equation reasoning. But I said, if you understand that means that the two equations on a graph should match, we could put this into a graphing calculator and also look at the table to see those answers. Let's go do that real quick. So I'm going to pull up Desmos and enter those equations we have. It was x squared plus, what was it, 8x plus 5. And we also had y equals 2x plus 5. Okay, so according to this graph here, where they intersect, where this parabola, you can see the first one's a blue parabola, where that one intersects with this green linear equation, the line, they should be our solutions. And you can see they connect right here at 0, 5, and they also connect at negative 10 and 25. And those were the two algebraic solutions we came up with the equation, 0, 5 and negative 10, 25. And you can see here, because of the parabola kind of going down and then back up, with a line cutting through it, it makes sense that the line's going to cross the parabola twice. Now, as we kind of think about different types of solutions that could happen, with our system, sometimes we had 2 solutions, sometimes 1, and even sometimes no solutions. You can think about what a parabola and line would look like that had no solutions. If somehow, if I change this linear equation, I'll see if I can tinker with it here, to be away from our parabola. Oh, not quite. Let's make it negative 100 or something. Oh, that's too much. Negative 10, negative 20. Oh, almost got it off there. Let's try negative 22. Oh, there we go. All right, now you can see this green line is not touching the parabola, the blue parabola, at all. And it may never. It may connect. We'd have to go back and do the algebraic equation parts to see if it will connect, but it's possible that they never connect, in which case it has no solutions. And also, if this green line just barely touched the parabola one time, then you would say that only had one solution. That's possible as well. But most commonly is the 2 solutions that we came up with today. So we're able to solve it with a graph. And of course, lastly, our graphing calculators have the ability to look at tables. If we were to look at the table and look at those values, here's back to the original one. If we were to look at the table values and go look at the value of negative 10 and see that the y was 25, and for the second equation, if it also had a x value on the table of negative 10, you can see both table values match at negative 10, 25, negative 10, 25. And the same happens here at 0, 5, 0, 5. They match on the table. So we can look at the table, we can look at the graph, and we can look at the equation. So we have 3 different ways to solve these quadratic systems. If this second equation was also a quadratic equation, we would do the exact same thing. We would still set them equal to each other, isolate one of the sides to become 0, and use our solving skills to solve for the quadratic equation. Well, that's it. I hope after doing a couple practice problems it doesn't seem as complicated and you get a little bit of the hang of it. And I hope to see you in class soon. Bye. Now for a word from our sponsor, Papercut Games. This week's game, Forbidden Island. Forbidden Island is a cooperative game, which is a little different than what you're used to, meaning everybody who's playing works together to try to beat the game board. You either all win together or all lose together. And it's kind of a cool game. The way you start out is all these little pieces, which you can see on the screen here, they're spread out and they kind of create the game board. So there's like 30 of them that create the game board, and as the game progresses, they start to flood. They turn to a water version of themselves, and then they eventually disappear. So the game board actually will start to flood and disappear underneath the player's feet, and every turn you kind of keep track of how much the island is flooding, and you're going to be using little meeples to walk around and try to stop the island from flooding. But most importantly, you're trying to capture these. There's 4 of these little I forgot what they're called, but they're like things you want to capture. They're like treasures of the island, I guess. And if you can work together to get all 4 of them and then get off the island before it floods, you win the game. But if you don't cooperate well, the island will flood and kill everyone, and you lose. So it's a fun cooperative game. You can see here it's only $19 on Amazon, and I have a good time playing it. So give it a try, Forbidden Island. I'm Mr. Bigsby, and I approve this message.